In geometry, a triangle means exactly what it means in standard English. Right? So you could reasonably look at this because the definition of the triangle here runs to a little over 2 lines. Right? I mean, you could reasonably say, okay, well, we know what it is. Why does the definition have to be so involved? And here's why. Right? Let's say we just said a triangle is a figure in a plane made up of 3 segments. Stop. Right? If we stop there, here's where we get into trouble. This is a planar figure made up of 3 segments. But that's not obviously not what we mean by a triangle. So, okay, we add this part here that says it has to be closed. Right? But that's still not good enough because this figure is made up of 3 segments in a plane and it's closed, but it's not what we usually mean by a triangle. A triangle shouldn't have these parts sticking out here. Right? So that's why we say, okay, they're only allowed to meet at their endpoints. Well, all right, so how about this? Made up of 3 segments. It's a closed figure. They only meet at their endpoints, but it's still not what we mean by a triangle. So that's why there's all this going on here. All right, this is what Einstein had in mind when he said, scientists try to make things only as complicated as they have to be to say what we mean. Right? And that's what's going on here. Right? Yes, there's quite a bit going on in this definition to define what it absolutely should be a pretty straightforward concept. But we need all of these bits and pieces to rule out all of these weird cases so that in the end, all we end up with are shapes that look like this, right? Our standard English language concept of a triangle. So once we've got this, right, we can classify triangles. One way that we do this is based on relationships between their sides, right? An isosceles triangle, like the one on the left here, is one with exactly 2 congruent sides. You notice how I've indicated this, right? These 2 little lines here are saying that those 2 sides have the same length, right? They're congruent. An equilateral triangle is one with 3 congruent sides, right? All 3 sides have the same length. And finally, a saline triangle is a triangle with no congruent sides. In other words, all 3 lengths are different. So one thing that's really interesting about triangles is that doesn't matter how you draw it. If you look at the measures of the 3 angles and you add them up, you're always going to get the same number. Doesn't matter how big or small the triangle is, doesn't matter what the relationship is between the sides are, it's always going to be the same number. And the proof of this, we're really not a proof-based class here, right? But the proof of this, I think, is pretty straightforward and kind of interesting. So I'm going to go through this real quickly here. What I'm going to do is I'm going to draw 2 parallel lines. I'm going to draw one of the lines going through one of the sides of the triangle. And I'm going to draw the other parallel line going through the opposite vertex. Right, now look at what happens. I have 2 parallel lines, and they're cut by 2 transversals, AC and BC. Right, that means that this angle up here is the same as this one down here. They're alternate interior angles. So this angle up top is equal to the measure of angle A. Then we get the same thing going on over here on the right-hand side. This angle and this angle are alternate interior angles, which means this upper angle is the same as the measure of angle B. And of course, the middle angle here is the measure of angle C, because that is angle C. And these 3 angles together make up a straight line. Right? So the measure of angle A plus the measure of angle B plus the measure of angle C is equal to 180 degrees. And that's our general rule, right? In every triangle, the sum of the measures of the angles is always going to be that value. So now let's see how we can use that that one piece of information to come to a lot of conclusions about a second way for classifying triangles based on their angles. So I've got three types of triangles here: an acute one, an obtuse one, and a right one. An acute triangle has three acute angles. An obtuse triangle has an obtuse angle, and a right triangle has, obviously, a right angle. So take a look at the diagrams here and see if you can't figure out which category each of these three belongs in. Right, so I think the middle one is kind of a freebie, right? That symbol means that's a right angle, and if it has a right angle, then it's a right triangle. Now there's one on the right here. If the bottom angles are 40 and 30, and it has to add up to 180, then this upper angle has to be 180 minus 40 minus 30 is 110. 110 degrees is an obtuse angle, so this one must be an obtuse triangle. And finally, this one over here. All three angles are the same, right? So turn this into a little algebra problem. If we add up the three angle measures, that comes out to 180. Well, this means 3x equals 180. So x must be 60. And that's all three of the angles, right? Each one is 60. 60 degrees is a right angle. So our triangle here is going to be the acute one. Now, you may have noticed that there are some combinations that didn't get included there. For example, is it possible to have a right obtuse triangle, right? A triangle that has both a right angle and an obtuse angle? Well, that can't happen, right? Because a right triangle means one of the angles is 90 degrees, and the obtuse angle has to be greater than 90 degrees. Well, if you add these two together, I don't know what it comes out to, but I do know that it's going to be strictly greater than 180 degrees, and that can't happen. We haven't even added the third angle in, and we've already exceeded the number that we know we have to end up on. So no, it isn't possible for a right triangle to have an obtuse angle. Right? And another thing that wasn't listed here, right, is well, our obtuse triangle definition is very specific. It says an obtuse angle, just one. Again, is it possible for a triangle to have two obtuse angles? Well, no, it isn't, and for really exactly the same reason. If the first angle is greater than 90 and the second angle is greater than 90, then if we add these two together, the result is already greater than 180 degrees. And again, we haven't even added the third angle in. So no, it's not possible to have an obtuse triangle, to have any triangle with two obtuse angles in it. So I really want you to file away that sum of the angles is 180 degrees property. That's a really, and as you saw, just from the few examples we did in the last slide, that's really kind of powerful property. And it's going to come up quite a bit as we go along and look at some other examples here. So in the next lecture, we're going to continue talking about triangles, and we're going to look at ways to tell when two triangles are the same.